Hello and welcome back to our channel. Today, we have a fascinating topic to discuss. Why do electrons in atoms occupy only discrete energy levels? Let's dive into the world of quantum mechanics to understand this intriguing phenomenon. As we know, atoms are the building blocks of matter, and they consist of a nucleus at the center, surrounded by electrons orbiting in energy levels or orbitals. But have you ever wondered why these electrons occupy only specific, discrete energy levels? Well, the answer lies in the principles of quantum mechanics. According to quantum mechanics, electrons exhibit wave-like properties and are described by the Schrödinger equation, which governs their behavior. This wave-like behavior of electrons leads to the phenomenon of quantization, where electrons can only exist in specific energy states. Quantization means that the energy levels in an atom are discrete, meaning they can only have specific, well-defined values. These energy levels correspond to the allowed energy states of the electrons in the atom. Electrons in atoms are arranged in orbitals, which are the standing wave patterns that represent the allowed energy states. These orbitals have specific shapes and energies associated with them, and each orbital can only accommodate a certain number of electrons. The reason for this discrete arrangement of energy levels is that electrons in atoms can only exist in stable, well-defined states. They cannot exist in between these discrete energy levels due to the quantized nature of energy in quantum mechanics. When an electron absorbs energy, it can move to a higher energy level or orbital, and when it emits energy, it can transition to a lower energy level or orbital. These transitions are responsible for the characteristic spectra emitted or absorbed by atoms, which are used in spectroscopy to identify elements and study their properties. The discrete arrangement of energy levels in atoms also explains why atoms have unique chemical properties and form chemical bonds in specific ways. The arrangement of electrons in discrete energy levels determines an atom's chemical behavior. In conclusion, the reason why electrons in atoms occupy only discrete energy levels is due to the wave-like behavior of electrons and the principles of quantum mechanics. This phenomenon of quantization leads to the specific arrangement of energy levels and orbitals in atoms, which determines their chemical behavior and characteristic spectra. I hope you enjoyed learning about this intriguing aspect of quantum mechanics. Don't forget to like, comment, and subscribe to our channel for more fascinating topics. Why big objects in space tend to be more spherical than smaller ones? Gravity, the attractive force between objects with mass, causes celestial bodies to collapse under their own gravity during their formation. As the object grows in size, the gravitational force increases, pulling material towards its center. Over time, this gravitational force causes the object to become more spherical in shape, as the material distributes itself evenly around the center of mass, minimizing gravitational potential energy. Additionally, the gravity of larger objects can exert a stronger tidal force on their own material, smoothing out irregularities and promoting a more spherical shape. This process is called relaxation and can occur over millions or even billions of years. On the other hand, smaller objects in space may not have sufficient gravitational force to pull themselves into a perfectly spherical shape. Their irregular shape could be the result of various factors, including their lower mass, weaker gravity, and less time for gravitational forces to act on them. It's also worth noting that some small celestial objects, such as comets and asteroids, can be irregularly shaped due to their composition and history of collisions. For example, comets are often described as dirty snowballs, because they are made up of ice and dust loosely held together, and their irregular shape could be the result of collisions or other processes. How does the amplitude of a matter wave relate to probability? In quantum mechanics, matter waves, also known as wave functions or probability amplitudes, describe the behavior of quantum particles, such as electrons, in terms of probabilities. The amplitude of a matter wave is related to the probability of finding a particle in a certain state or location. According to the Copenhagen interpretation of quantum mechanics, the square of the magnitude of the matter wave's amplitude at a particular point in space gives the probability density of finding the particle at that location. In other words, if the amplitude of the matter wave at a certain point is larger, the probability of finding the particle at that point is also larger. Conversely, if the amplitude is smaller, the probability of finding the particle at that point is smaller. Mathematically, if we denote the matter wave as psi, x, where x represents the position of the particle, then the probability density p, x, of finding the particle at position x is given by p, x. equals psi x squared, where psi x squared represents the squared magnitude of the matter wave's amplitude at position x. It's important to note that the probability density is always a non-negative real number, and the total probability of finding the particle in all possible locations must be equal to 1. In summary, the amplitude of a matter wave in quantum mechanics is related to the probability of finding a particle in a certain state or location. The larger the amplitude, the higher the probability of finding the particle at that location, as described by the squared magnitude of the matter wave's amplitude, which represents the probability density. If Planck's constant, h, were larger, would atoms be larger also? Defend your answer. If Planck's constant, denoted as h, were larger, it would not directly affect the size or dimensions of atoms. The size of atoms is determined by the balance between the electromagnetic forces that hold the electrons in orbit around the nucleus and the repulsive forces between the negatively charged electrons and the positively charged nucleus. This balance is governed by the fundamental forces of electromagnetism and quantum mechanics, which are described by other fundamental constants and principles. Planck's constant, on the other hand, is a fundamental constant of nature that relates to the quantization of energy and the wave-particle duality of matter and energy, as described by quantum mechanics. It appears in various equations, such as the Heisenberg uncertainty principle and the quantization of energy levels in atoms, which determine the allowed energy states of particles in a quantum system. Changing the value of Planck's constant would alter the behavior of particles at the quantum level, including the energy levels of electrons in atoms. However, it would not directly affect the size or dimensions of atoms, which are primarily determined by the balance of electromagnetic forces between electrons and the nucleus. It's also worth noting that Planck's constant is an extremely small constant, with a value of approximately 6.626 times 10 to the minus 34 joule-seconds in the International System of Units, SI. Any significant change in its value would have far-reaching consequences for the behavior of matter and energy at the quantum level, potentially leading to a fundamentally different physical universe. However, there is currently no experimental evidence or theoretical basis to suggest that Planck's constant could have a different value than what is currently accepted in modern physics.